Hello and welcome to the scientific adventures of Beard Man. Today we're going to be looking through a concept builder on physicsclassroom.com. It's in the topic electric circuits and the title is Know Your Potential. Potential refers to electric potential difference, also more commonly known as voltage. Okay, we're also going to look at electric potential a fair amount in this particular concept builder and talk about the difference in the electric potential in different places in the circuit. So, electrical potential difference is the difference in energy per coulomb of charge. So, in other words, how much energy does each electron have on either side of an object, such as a resistor like a light bulb? How much energy do we have over here compared to over here? Or on the two sides of a source, like a battery, over here compared to over here. So the idea is how much energy does each electron gain moving through the battery, or how much energy do they lose going through the light bulb? Remember, the energy they lose is turned into another form of energy because of conservation of energy. And in this case, it has become heat and light. In the case of a light bulb, it becomes heat and light. Of course, it does processing in your computer and it does all kinds of different things, makes things spin in electric motors and so forth. Okay, gives them mechanical energy. Then finally, don't forget that conventionally we imagine a positive charge is moving. Okay, if you're familiar with batteries, you know that this is the positive side of a battery and this is the negative side of the battery. Okay, so if we were talking what's really going on, which is that the electrons are going to move, those electrons have high energy over here. You can think of it like there are a bunch of electrons really close to each other. Well, they don't like being really close to each other, so they want to spread out. So that's going to push the electrons through the circuit this way, up through the light bulb. As we looked at light bulb anatomy, this bottom thing is connected to one of these filaments here. It's going to push the electrons through the filament, which is where they lose their energy and turn it into light, and back down, connected to the side and around to the positive end of the battery. Over here, having less energy being pulled this way by, you could think of it as a lack of electrons, a positiveness there, and that will pull them in there. Okay? But as we said, remember, conventionally we imagine positive charges flowing. Okay, so that's going to flip everything around because we're thinking of it in terms of positive charge, even though there are electrons flowing. By the way, there's so many things that deal with positive charge, from right-hand rules to ways that different circuits work to electromagnets and things like that, that it would be one of those things that's difficult to change. Just like America should be using the metric system, but we keep using feet and inches because it's pretty hard to change. Anyways, so that means that instead of this side being considered the high energy side, the positive side will be the high energy side because positive charge is considered moving. When we talk about conventional current, it's imagined that way. So this is our higher energy potential, higher electric potential, meaning it has more energy there, the current, and this side has less energy because it's connected to the negative. Now, anywhere that's connected directly to the negative, let's see what that one does. Anywhere that's connected to the positive, oh, I don't like that. Let's use that. Anywhere that's connected to the positive is going to have higher energy. Okay, so this is connected to the side here. So all the metal on the side there will have higher energy. And then up along there, that wire will have the higher energy as well. Why? Well, going back to talking about electrons moving around, if charges have more energy anywhere along here and less energy somewhere else, they're just going to flow there and kind of clump up there. And so they'll spread themselves out so that all the energy along here is equal. Now, in reality, there is some resistance in here, and that will change the energy. But for our purposes in beginning looking at electric circuits, we'll just say all this metal has no resistance whatsoever, and therefore all of this has exactly the same energy. And that's what you'll see in this concept builder, as well as in most high school physics classes, and even some introductory college physics classes. All right, so then as it begins to go through the filament here, that energy is going to decrease. So we'll represent that as going from yellow, or from red to yellow. Then where the red and yellow overlap there, it looked a little bit like orange. That's actually perfect. We'll talk about that later. And then it'll become green as it continues to move through there, getting less and less energy, because it's the energy of each electron is being taken away, or each charge is being taken away. And so then eventually it gets to blue, where it's at low energy. We'll actually consider that 0. And it'll go through the center of this. It won't actually touch that metal there. So let's keep that metal red. It's going to look kind of purple now. Anyways, but the blue is going through the center. It doesn't actually touch that metal. It comes down and touches this metal at the bottom, which then all of this is all connected. So once again, it'll all be at the same energy. It'll be the energy of our side over here, which we'll define as being 0, kind of like defining your frame of reference. This will be defined as 0 because it's the lowest the energy gets in this circuit. So now let's take a look at the first 2 activities that we see in this concept builder. Their titles are Color Those Wires and Which Bulbs Light. We'll start off with what happens in Color Those Wires, but both of them have circuits like this in the same general setup. So we remember that the long side of the battery, oh, maybe you don't know this yet. The long side of this battery is the positive side, and the one that ends with a short side is the negative side of the battery. Okay, so everything attached to the positive side of the battery, you'll end up clicking on. You'll click down here on red, and then you'll click on this wire up here, and it'll turn red because it's attached to this battery. But remember, all the wires that are connected to that battery, all of these have the same electric potential. Okay, meaning each charge has the same amount of energy. But then when the electrons or the charges have to go through the light bulbs, by the way, these circles represent the light bulbs. When they have to be pushed through it, they're going to give off some light, right? And that's going to take away their energy. So they'll have less energy per charge, which means the wire beyond that will have less energy. I'm going to make it orange by making it red and yellow. Okay, so this part will be orange. Then as it pushes through this next light bulb, then it'll become yellow. And as it pushes through the final light bulb, it'll become green. Okay, you may have noticed that I went this direction instead of this direction. The reason is this only had 1 light bulb to get to this light bulb. This one had 3 light bulbs. So I need to make sure that I could change colors through the spectrum from red to orange to yellow to green. The same order they're in here: red, orange, yellow, green. Okay, and then the green one we're on here, since it's connected to this wire, this is going to be all green as well. Then through our final light bulb here, right attached to the negative side of the battery is blue. You could do this second right after the red. Just label this blue, and you're all set to go. So now that is all you have to do for the Color Those Wires activity, like the apprentice level. But the master level, Which Bulbs Light, has you do this with the colors, and then it also asks you to light up the bulbs that would light up. Well, this first light bulb has energy, charges that have the energy of the positive side of the battery, so the high energy. It actually has the same energy on both sides of the light bulb. Well, what makes electrons move from one side of a light bulb through the light bulb and give up their energy is a difference in energy. They're trying to get to a place where there's less energy. So they push through that filament, giving off the energy of the light bulb. So when we see that happen, like we see here, going from red to orange, that one will light up. Or here, going from orange to yellow, that's a decrease in energy, which means the electrons will be pushed through and it will light up. Or here, going from yellow to green, that one will light up. Or this one going from red to green, that's a big difference in energy. So that might be our brightest light bulb of them all. And then finally going from green to blue, that's a difference in energy. So it'll light up. It'll give off its energy in the form of light. But This one up here, neither side is being pushed any more than the other side. You could say both sides have the same amount of pressure pushing against them. So the electrons don't flow through this, and therefore this light will remain off. You don't actually write off, you just leave it unlit up. Okay? All right, as you can see, when you do it in the thing, tapping on the bulb will toggle the lights on and off. All right, so that's the first two levels of the concept builder. The next level, we need to take a look at Ohm's Law. In Ohm's Law, we see the three variables that we've been looking at all connected in one equation. We see the current, which is I, which is how much charge flows past a point each second, measured in amps or amperes. We see the voltage. Voltage is how much energy each charge has. That's what we're learning today, measured in volts. Sometimes you will see that as a lowercase v. And resistance, which we've already talked about, how much a substance resists the flow of charge, measured in ohms. We had not mentioned it was measured in ohms. It's kind of fun to say ohms. You might put your thumb on your middle finger on each hand, point your palm to the sky, cross your legs in lotus position, and close your eyes and say om. As those monks try and get rid of the resistance to their soul, it reminds us that ohms are a measurement of resistance. Anyway, it's kind of fun. But we see the relationships here too. We see that if we increase the voltage, it's in the numerator. If we push harder on the charges, give them more energy, they will go faster through the circuit and we will have a larger current. However, resistance is in the denominator. If we have a substance that is very hard to flow through, the harder it is to flow through, we're going to divide by a big number. That's going to make it for a very small current when it's very hard to flow through. So we see all the relationships we've talked about all wrapped up in this wonderful little tidy equation. Sometimes people prefer to multiply both sides by r, in which case you get this equation down here. And since today we're going to be solving for voltage or electrical potential difference, we will want to use the equation down here at the bottom. In our first example here, we can see that we can go through and mark where our high energy is. So from the positive side of the battery, we see that part will be red. After it goes through, it'll lose some energy, and then we'll have orange, which I make by using red and yellow together. Okay, so we have orange there. Then as we push through that, we get yellow over here. Then once we push through the next one, we get green. We see that's going to connect all these. So this middle one here will hit green right away. And finally, on the negative side of the battery, we have blue. So if we go ahead and go through this, now we can start marking what the electric potential is at various places. So as you come through the battery, as electrons or charges move, the current moves through the battery, it picks up electric potential. It gains 48. So we'll go ahead and jot down 48 here. Once again, that's 48 volts. We can see that it's written in volts. So down at the bottom, you just write the number. And of course, that's because we picked our lowest place to be 0 volts. 0 volts. And so that's our lowest place. That's our frame of reference. So now how much energy do we lose going through the light bulb? Well, let's use Ohm's law. V equals IR. Okay, so we see we have I, which is 7 amps. We have R, which is 2 ohms. I times R, 7 times 2, gives us 14. So we had 48. We lose 14. That will give us an electric potential of 34 volts. 34. Then as we go through the next light bulb, I times R, 7. I meant to do that with the laser pointer. As we go through the next one, we see 7 times 2, that's 14 again. So 34 minus 14 gives us 20 volts. So the yellow section here will be 20 volts of electric potential. And as we go through this next light bulb, we're going to lose energy. It will become light. the current loses it, or the charges lose it, but it becomes light and heat. 6 amps times 2 ohms, that's 12 volts are lost. So that leaves us with 8 volts right here. And notice D and E are both in this green section of 8 volts. But we can double check our work. We can see going from orange to green, we should lose 2 times 13. We should lose 26. 34. Losing 26 does give you 8. One more double check. Let's make sure we get to 0 going through this last one. We see 4 times 2, that's 8. 8 minus 8 does give us 0. And then finally, the battery pumps up the charge to give it 48 volts of electrical potential when it gets to that point. Okay, so just to quickly review, we learned Ohm's law, that the current is affected by the voltage and the resistance. So we had I equals V over R. As the voltage increases, that makes the current increase. As the resistance increases, that decreases the current. We rearrange it. And for this exercise, this is the easiest way to use this equation. All right. And then if we go back, we also learned about electric potential, okay, that when the battery pumps up the energy of the charge, all the metal connected to that has that same potential essentially. We pretend that for now. Then it loses potential as it goes across the filament, and then the low potential, electrical potential, is on that side connected to the negative side of the battery. Remember, this is all based on conventional current. All right, enjoy puzzling out your concept builders, and hopefully you learn a lot about electrical potential and Ohm's law. Hope you get a charge out of this one. Don't forget to hit that subscribe button, and we'll see you next time on the scientific adventures of Beardman.